Hello, I'm Kirk Weiler, and this is Common Core Algebra 2 by eMath Instruction. Today, we're going to be working on Unit 10, Lesson number 13, Solving Rational Inequalities. Now, before we jump in and get into the details of how you solve inequalities that involve rational expressions, I don't want you to ever forget that when you solve an inequality, or an equation for that matter, you're trying to find all values of x that make the inequality or the equation true. All right? So really, if I give you an inequality and a value of x, you should always be able to tell me whether that value of x makes the inequality true or false, and therefore whether it's in the solution set or not. Don't forget that, because we're going to emphasize that a lot in the first portion or in the first problem, and you really have to kind of have a firm control over that before you get into all the little details of how to solve these problems. All right, let's jump into the first exercise. All right, exercise number 1 says consider the rational inequality x minus 5 divided by x plus 3 is greater than or equal to 0. All right, so ultimately, I want to find all the values of x that make that a true statement. Letter A asks us, at what value of x is the ratio equal to 0? Is that part of the solution set? What I'd like you to do is pause the video now and try to answer both of those questions in letter A. All right, well, let's go through it. So in order for any fractional expression or rational expression to be equal to 0, the numerator must be equal to 0. Of course, I can solve that in my head, as you can as well, and we get x equals 5. Now the question is it part of the solution set? Well, if you can tell that without doing any more work, that's great. But if not, there is always one check, which is that we put it into the inequality and we see if it makes it true. All right, now what that gives us is 0 divided by 8 is greater than or equal to 0. Of course, 0 divided by 8 is 0, so we get 0 is greater than or equal to 0, and that is, of course, a true statement, because 0 is equal to 0, right? It's all about that equality sign, and therefore the answer is yes, it is part of the inequality. Okay, all about that little equals being included. Now, letter B asks a very similar question. At what x value is that ratio undefined? Is this value part of the solution set? Again, pause the video and try to answer both of those two questions. All right, well, in order for any fractional expression to be undefined, rational expression to be undefined, the denominator, what you're dividing by, has to be equal to 0, in which case we get the value x equals -3. Again, if you know off the top of your head whether that is or isn't part of the solution set, awesome. If not, you would simply substitute it into the inequality and test it. Is that greater than or equal to 0? Well, if we do the arithmetic, we get -8 divided by 0 is greater than or equal to 0. Now here's where you have to be a little concerned, because -8 divided by 0 doesn't have a value. It's undefined. So can a number that's undefined be greater than or equal to 0? And the answer is no, of course not. I mean, it's not even a number, right? So that's a false inequality, and the answer must be no. All right? So obviously there's something important about both 5 and -3, and we're going to investigate that now by using our graphing calculators. Let's bring out the TI-84 Plus. All right. Now, what I'm going to do is I'm going to use it not to graph this expression, although it's going to start to feel that way at the beginning, but to just simply see for any given x value, is that ratio x minus 5 divided by x plus 3, is it positive, is it negative, is it 0, is it undefined? That's what we're going to be looking at. So let's go into y equals. All right, if you have any equations in y1 or y2, etc., clear them out. All right, now in y1, what I'm going to do is I'm going to put that ratio in. Now, I don't have any fancy fraction like mode turned on, so I'm just going to put parentheses, x minus 5, parentheses, divided by, parentheses, x plus 3, parentheses. Now, it's very, very important that you have those parentheses in there unless you have sort of fraction mode turned on where you can clearly see what's in the numerator and clearly see what's in the denominator. Okay, so make sure that they're in there. Take a moment. All right, let's pop into the table now. Okay, actually, let's pop into table setup. Table setup. So go into table setup. And what I want to do is investigate for a variety of different values of x whether or not that ratio is positive or negative. So I think I'll start my table at -10, and I'll make it go by ones. That's fine. So start at -10, going by ones. And now let's actually go into the table. Now, what you see, sorry, I have to cheat a little bit and look down at my calculator over here, is at -10, right, when I have this table, make sure we can identify x and y1. When I have an x value of -10 and I have that ugly y value of 2.1429, I don't care so much about the actual value. What I care about is the fact that it's positive. All right? And that means -10 must be part of the solution set because it makes it true. So actually, let me go down in the table a little bit. Right? When I go to -9, the output, the y column, is still positive. When I go to -8, the output, the y column, is still positive. In fact, as I go down in that table, it takes a little while on this calculator, as I go down in that table, what I see is I continue to see positive outputs until I hit x equals -3. And at x equals -3, and this is very predictable from letter B, I see an error because it makes that fraction undefined. But what's really cool is when I go to x equals -2, right? What do I have there? I've got an output of -7. When I go to x equals -2 and I have an output of -7, that's negative. So that means my inequality is false there. Okay, it's false. So -2 is not going to be part of the solution set. And when I go to -1, I see that the output is negative. And when I go to x equals 0, I see the output is negative. And x equals 1, the output is negative. X equals 2, the output is negative. In fact, I have to keep going down in that table until I hit x equals 5. And then the output is 0, which I knew from letter A. The cool thing is, now if I look at x equals 6, now the output has turned positive again. And at x equals 7, the output is positive. And at x equals 8, the output is positive. In fact, I can keep going down in that table as far as I want, and the output will remain positive. So I'm going to draw a little number line to really summarize everything that I just saw in my graphing calculator's table. I'm going to mark that -3, and I'm going to mark that 5. I'm not going to put anything else on this number line. Please don't. I'm going to put an open circle at 3 because the expression is undefined there. And I'm going to put a closed circle at 5 because I know it's part of the solution set. What I saw was that all the outputs were positive for numbers that were less than -3. The output was all negative when the numbers were between -3 and 5. And the outputs were all positive when the x values were greater than 5. Now what I wanted was all values of x that gave me outputs that were greater than or equal to 0. In other words, positive. So those would be all those outputs. And therefore, my solution set is all values of x such that x is less than -3 or x is greater than 5. Oops. And I just made a little mistake there. It should be x is greater than or equal to 5, but now you can probably barely see that. So let me just erase this so it's very clear. Greater than or equal to 5. All right. So clearly there was something very important about the zeros of this expression, i.e. what made it equal to 0, and what made it undefined. Now let's talk a little bit before we go on to the next exercise why that's happening. Now, don't forget that fractions ultimately are division. And whether or not division turns out to be positive or negative depends on whether the numerator is negative, or the denominator is negative, or the numerator is positive, denominator is positive. We all know that a negative divided by a negative is a positive. We all know that a negative divided by a positive is a negative, etc., right? So let's say you picked a number like x equals -4. and you substituted it into this expression, you'd get negative 4 minus 5 divided by negative 4 plus 3, and that would get me negative 9 divided by negative 1. The point really isn't negative 9 divided by negative 1, it's negative divided by a negative, and that gives you a positive. But then if you pick a number between negative 3 and 5, I gotta find some space here. Let's say we pick x equals 0. That's a good choice. Then we would have 0 minus 5 divided by 0 plus 3. Again, it's not really important what we get. What's important is that the numerator is negative, the denominator is positive, and that results in an overall negative. Finally, if we pick a number in this area greater than 5, let's say x equals 6, that's convenient, and we substituted it in, we'd have 6 minus 5 divided by 6 plus 3. Again, not really important what the final answer is, but the numerator is positive, the denominator is positive, and we all know that a positive divided by a positive is a positive. All right? And therefore, we get that solution set. Let me be very clear. The final answer to this problem is this, and to a certain extent, this number line. This is the graphical answer, and this is the algebraic answer. All right, pause the video now and really take all of that in before we introduce a new piece of terminology. All right, I'm going to clear out the text, and let's learn about what's known as a critical value. Critical values are values of the input, so they're x values, that are either zeros of the expression or make the expression undefined. Okay, zeros of the expression or make the expression undefined. So that last expression, x minus 5 divided by x plus 3, x equals 5 is a 0. All right, when we already saw why that was, because when we substituted it in, we got 0 divided by 8, which was 0. All right. On the other hand, x equals negative 3 made the expression undefined, because when we substituted it in, we got negative 8 divided by 0, which is a problem. You can't divide by 0. You'd be crazy to try to divide by 0. So the point here, though, is that 5 and negative 3 are both critical values of this rational expression. And critical values are going to, pun intended, are going to play a very critical role in solving rational inequalities. So let's take a look at how these things work. All right, exercise number 2. Solve the rational inequality x squared plus 3x minus 4 divided by x squared minus 6x plus 9 is less than 0 for all values of x. Show your solution on a number line and state its solution in either interval or set builder notation. All right, great. We want to find all the values of x that make this ratio negative. All right, and the first thing I'm going to do, apparently in red, is I'm going to find the zeros. All right, I'm going to take that numerator and I'm going to set it equal to 0. All right, I'm going to use the zero product law. That'll work out well. And I'm going to get x equals negative 4 and x equals 1. So these are critical values. They're going to show up on my number line. Then I'm going to find the ones that make it undefined, because they're also critical values. That's a little bit more difficult, right, than in the last problem. It's not more difficult than finding the zeros. All right, and this one factors kind of interestingly, right, because it factors as x minus 3 and x minus 3. So we set x minus 3 equal to 0, and we just get x equals 3. So there are my critical values, negative 4, positive 1, and positive 3. Now what I'm going to do is I'm going to draw out a number line, all right, and I'm going to label all my critical values. I'm going to put negative 4, positive 1, and positive 3. Okay. For me, the next thing that I do is determine if any of those critical values lie in the solution set. Now, one thing is for certain. Wherever there is an expression that's undefined, it cannot lie in the solution set. So I'm going to put a little open circle there. The question is, do the zeros fall in the solution set? And in this case, they don't because there is no equality when we're comparing this to 0. So I'm also going to put open circles here and here. Now, what I'm going to now do is pick x values in each one of these intervals and test them in my inequality to find out if it's positive or negative. And I'm going to actually test it in the factored form of the inequality. Here's the factored form of the expression. X plus 4 times x minus 1, all divided by x minus 3 times x minus 3. So let's take a look at how this works. Let's say in this area I pick x equals negative 5. Okay, if I put it into the first parentheses, negative 5 plus 4, I get negative 1. Now I'm not going to write down the negative 1, I'm just going to write down a little negative. On the other hand, if I put it in this parentheses, I get negative 5 minus 1, which is negative 6, and I also get a negative. If I put it in this parentheses, negative 5 minus 3 is negative, and obviously also a negative. Now remember, this is multiplication up here and division overall. A negative times a negative is a positive, and also a positive, and then a positive divided by a positive is a positive. So any number I pick in here is going to give me a positive. All right. Let's try x equals, well, 0. That lies between negative 4 and 1. Let me put it into the first parentheses, and I get a positive. Then in the second parentheses, and I get a negative. Then in the denominator, I get a negative, and I also get a negative. Again, remember that's multiplication and division. A positive times a negative is a negative. A negative times a negative is a positive, and a negative divided by a positive is a negative. So any number I pick in here is going to result in a negative. Let me go with an x value in here. Let's go with x equals 2. If I put it in the first parentheses, I get a positive. Second parentheses, I get a positive. Then I get a negative and a negative. Again, multiplication and division gives me a positive in the numerator and a positive in the denominator, which overall gives me a positive. Now be careful. So far, it looks like the signs just alternate. But watch what happens when I pick x equals 4. When I put it into the first parentheses, I get a positive. The second one, I get a positive. In the denominator, I get a positive and a positive. And a positive times a positive is a positive. And then the denominator, I also get a positive, which gives me a plus. So there the sign didn't alternate. Now that has to do with the fact that that x equals 3 was a double root. A double root. Signs don't tend to change at double roots. They would at a single root or triple root, but not at a double root. Now, after all was said and done, what in the world am I coloring in? I want to color in all values of x that resulted in this being less than 0. In other words, that resulted in it being negative. So I'm going to do that in red. Here's my solution set. Everything from negative 4 to positive 1. So there's my graph of it. In interval notation, it would look like this, negative 4 to 1. And in set builder notation, it would look like this. Whichever you like better. So let me put an or there because you don't need them both. All right, that's actually how we're going to do almost every one of these problems. All right, there's going to be a little wrinkle in a moment that's going to be a bit irritating, but you'll roll with it. It'll be fine. All right, pause the video now and write down anything you need to. Okay, I'm going to clear out the text. All right, exercise number 3. Solve the rational inequality x divided by x minus 8 is less than or equal to 5. Represent your answer using a number line and using set builder notation. All right, so what we're going to do in this case is, because we're comparing this to 5, what I really want to do is I want to compare it to 0. And that means I've got a little bit of work to do before I even start with anything else. So what I'm always going to do with rational inequalities is I'm always going to attempt to compare them to 0. So I'm going to move that 5 to the other side, and then I want this all as a fraction. So what that means is I've got to do a little bit of common denominator work, right? The common denominator is x minus 8. So I'm going to just do some common denominator work on the back side of my sheet. All right. And that's going to give me x minus 5x plus 40, all divided by x minus 8, less than or equal to 0. And that's negative 4x plus 40 divided by x minus 8 is less than or equal to 0. All right, so no problem. All I did was took this inequality and wrote it equivalently as this inequality. All right, let me check my work. Good, it all looks good. One thing that's particularly tricky is the fact that you've got this double negative here. That worked out okay. So now let's take it right from here. All right, the first thing I'm going to do is find my 0. Okay, and my 0 I'm going to find by setting that numerator equal to 0. And that's pretty easy. We get negative 4x is equal to negative 40, and x is equal to 10. We also want to figure out where the thing is undefined. And it's going to be undefined whenever x minus 8 is equal to 0, or x is equal to 8. So those two are pretty close together, but that's okay. It's not a problem on my number line. Far away, close together, I don't really care. I've got 8, I've got 10. Remember, wherever it's undefined, it cannot be part of the solution set. It just can't. So I'm going to have an open circle there. How about that 10? Well, the 10 will be part of the solution set because the equality actually is contained in the solution. All right? So now I want to start testing numbers. Now, again, I can certainly test this in the factored form of this inequality. The factored form would kind of look like this. You know, if I factored a negative 4 out, it would look like this. There's nothing wrong with using this. In fact, watch, let's do it. Here's my factored form. Let me pick x equals 7. Right? If I did that, I can't forget the negative 4. That's that negative right there. But then if I put the 7 in parentheses, I'd also get a negative. And then if I put it in the denominator, I'd also get a negative. So that would be a positive divided by a negative, and that would be a negative. All right? Then let's say I picked x equals 9. Remember, I don't want to forget that negative 4. But then if I put it into that parentheses, I'd also get a negative. And then if I put it in the denominator, I'd get a positive. A negative times a negative is a positive. And a positive divided by a positive is a positive. So there we see the signs alternating. All right. Finally, let's say I took x equals 11. If I substituted it into the numerator, I'd get a negative from that negative 4. Then I'd get a positive when I subtract 10. And then I'd get a positive in the denominator, which would give me a negative divided by a positive, which would give me a negative. All right? So what am I looking for? I'm looking for all values of x that make this inequality less than or equal to 0. That means it would be out here, and it would be out here. All right? So I'm going to use set builder notation. I'm going to say all values of x such that x is less than 8 or x is greater than or equal to 10. All right. And that's it. Now, the irritating part about this one is having to convert it so that we compare it to 0. But if we go through that process, right, then it's all just about finding the critical values and then finding numbers and substituting them in to test the inequality. So pause the video now and look at all the work that we did. Okay, I'm going to clear out the text. And let's do one last problem. All right. Now, you just have to sort of keep your wits about you when you do problems like this. and you have to just work it so that you get it compared to 0. All right. Now, in order to do that, right, I want to compare this inequality to 0. The first thing that I would do is I would move my 3/2 to the other side, because then I have an inequality compared to 0. Now, I want it to be all one fraction, so I have to get a common denominator. And that common denominator's got to have a factor of 2, it's got to have a factor of x plus 3, and it's got to have a factor of x. So the common denominator I'm going to be looking to get is this. That's going to be my least common denominator. So let's take that first fraction. The first fraction, in order to have that denominator, I've got to multiply the numerator by 2 times x plus 3. And the denominator, obviously, by the same, but once I do that, i.e. I multiply by x plus 3 and 2, this x was already there, then it's got that common denominator. The second fraction, I'm going to have to multiply top and bottom by 2x, because it's already got the x plus 3. Whoops, my mistake. That should be an x plus 2. Right. And the last one, I'm going to have to multiply the numerator and denominator by x and x plus 3, because it already has the 2. And now we have a common denominator. Oh, there's going to be some work to be done here, though. Wow. Oh my goodness. Let's see what we have. Okay, well, we all have a common denominator now, 2x times x plus 3. All right, so I can put down a single denominator, but now I have to multiply stuff out and combine like terms, and oh my goodness. Okay, but here we go. This is going to be the most challenging of all of them, because I have three-way multiplication, x minus 1 times 2 times x plus 3. All right, so I think I'll leave that 2 out until last, and I'll multiply the x minus 1 and the x plus 3. That's going to be x squared plus 2x minus 3. All right, might as well multiply this out. That's going to give me 2x squared plus 4x. And watch out, we have a subtraction here. So that's going to give me negative 3x squared minus 9x is less than 0. Keep going. All right, just have to keep working this problem down. Here we'll have 2x squared plus 4x minus 6 plus 2x squared plus 4x minus 3x squared minus 9x is less than 0. Wow. We're not going to have any room to just do the inequality here. So let's combine like terms in the numerator. We have 2x squared, 4x squared, minus 3x squared gives us 1x squared. All right, so that takes care of this, this, and this. Let's take a look at our x's. 4x and 4x is 8x, minus 9x gives me negative x. That takes care of this, this, and this. And then we have that negative 6, all divided by 2x times x plus 3. Now again, you might be wondering, why am I not multiplying out the denominator? Well, eventually I want to know the zeros of the denominator. So first, let's find the zeros of the numerator, which are the zeros of the overall expression, x squared minus x minus 6 equals 0. Then I'll just factor this, and I'll get x minus 3 and x plus 2. And I'll get x equals 3 and x equals negative 2. All right, we also want to figure out where it's undefined, and that's going to be wherever 2x times x plus 3 is equal to 0. So that's going to give me 2x equals 0, and x plus 3 is equal to 0. X equals 0, and x equals negative 3. Wow. So look at all the critical values we have. 1, 2, 3, 4. And a lot of algebra to get to those critical values. Wow, wow, wow. Anyway, let's put them on our number line. We've got negative 3 there. We've got negative 2 there. We've got 0 there. And we've got 3 there. Let's do open circle, closed circle kind of thing. All right, they're actually all open circles. And they're all open circles because at x equals 0 and negative 3, the expression is undefined. And at x equals 3 and -2, it's equal to 0, but the equality is not in there. Now, I'm kind of running out of space, and it's gotten to be sort of a long video, but we would continue to check all those values of x, and we'd find that we had a positive there, a negative there, a positive there, a negative there. In fact, all of these do end up alternating, and a positive there. So if we take values of x in between all of these and substitute them into this inequality, that's what I would work with, this inequality, because that's the one that's compared to 0. That's the sign analysis that you'd get. And what we're looking for is we're looking for values of x that make that expression less than 0. So let's actually color that in red. It's going to be less than 0 here, and it's going to be less than 0 here. So at the end of the day, I'm going to write this in interval notation. Our solution set goes from -3 to -2, union from 0 to 3. So that is our final solution set. So what we can do in just a moment, after we've kind of paused the video and you've looked at everything on this page, because there's a lot going on this page, is I can then clear out all the text and we can kind of wrap this up. So pause the video now and think about what we did on this page, and then we'll clear it out and finish it up. Okay, let me clear it out. All right, so rational inequalities, undoubtedly the hardest inequalities that you're going to work with in this course. It's all about really two things. Comparing the inequality to 0, so you might have to rearrange and do a little bit of algebra in order to do that. And also finding the critical values, those values of x that make the numerator equal to 0 and the denominator equal to 0. Once you plot those on a number line, then it's all about testing values of x that are in between those critical values to see if they make the inequality true or false. All right. Well, thank you for joining me for another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.